Hi, my name is Nicholas Wiley, and today we are going to be applying Bernoulli's principle to a sealed leaking tank. So let's first discuss our system that we have as I've drawn. Now, when we're first discussing a system, it's important to denote all of our parts of the system. So let's just get right into that. So what we're going to have first is we're going to have the total height of our tank, which we are going to call H total height. What we also have is we have this fluid height, which I'm going to call little h. This is going to be a variable that we are going to be looking for an equation for. Either way, let's move on. We also have our cross-sectional area, which is big A sub c. I usually like to do big C sub A because you say cross-sectional area rather than A sub c. Either way. Then what we also have is we have A sub hole. It's going to be this hole, this very small hole that you can barely see. That's what fluid's going to be leaking out of. Now, when looking at this system, there's a couple things we need to keep in mind why we can be using Bernoulli's principle for this. What we need to know is that the height of our fluid in this case is going to sort of be modeled like this. It's going to, maybe not that quick of a drop, but the fluid is going to be dropping until it hits a steady state, which is what Bernoulli's equation is about. And why is the system going to be steady state? We have a few things that we can keep in mind. What we know is that no air is going to be coming in through this hole up to our system, which is very useful for us. Mess that up a little bit. In addition, we know there's no frictional heating. This doesn't have to do with steady state, but I'm just going to run through some assumptions that we have. There's also going to be no vapor pressure. That really helps us. We are going to be neglecting the vapor pressure of our fluid on our system in this case, which does help. And then in addition, we are going to be neglecting any temperature changes that may occur throughout the system. But either way, what we're going to be doing is we're going to be modeling this height change of our fluid as steady state, which is why we can use Bernoulli's equation. Just thought I'd get that out of the way. Now, what are some other things? I ran through the assumptions. I guess there's a couple other things that we can try and keep in mind. When we're modeling this system, what we're going to have is we're going to have this position 1 right here, the top of the fluid, and we're going to have our position 2 at the bottom of the fluid. Okay, and I'll get to why that's significant in a few minutes and what we are going to denote those as we get into Bernoulli's equation. Another thing to keep in mind is we're going to be assuming that this air in here is going to be at atmospheric pressure, and in addition, there's only going to be an n amount of moles of air that is going to be in here, as I've said, due to the fact that no air is going to be coming into our system, one of our assumptions due to the surface tension of water. But either way, I think we've gotten enough assumptions out of the way. If I forgot anything, I'll be sure to run back through it as I get into actually Bernoulli's equation and trying to figure out some expressions for the terms that we have in there. So what is Bernoulli's equation? What we're going to have is the frictional heating, which I just do a cursive F. I can't draw it as fancy as all the other students and people out there. That is going to be equal to a pressure difference, our pressure at point 2 minus our pressure at point 1. It's going to be over rho, the density of our air. What we're going to have is the change in kinetic energy, which is going to be V2 squared minus V1 squared over 2. And then what we're going to have is we are going to have our gravitational constant multiplied by Z2 minus Z1, which we are just going to call the change in height. Okay, so when looking at this, the best way to approach this is to just start going in at it. We're going to go piece by piece, and we're going to find some zeros. We're going to find some things that we can simply substitute in. And in the end, we should be left with how the volumetric flow rate, we should be left with the volumetric flow rate equation that will lead to the differential change in height over time, which we will not get into yet. That'll be towards the end of the video after we've gone through everything. Okay, either way, the first thing that we should talk about is the continuation equation. So what does that mean? Well, what we're going to say is that the flow rate that is going to be the cross-sectional area, the flow rate is going to be our differential height multiplied by how much the fluid level is sinking. And this is going to be equal to the cross-sectional area of our hole down here multiplied by the velocity at point 2. Now it's important to note for this. So what we have is we have a cross-sectional area which is going to be so much larger than the cross-sectional area of our hole, which you can barely even see that hole, and then this is a very large tank. So what we can say is that since this is so large, V1 has become negligible as it becomes 0. So that's going to be a very nice assumption for us to have, is V1 is going to be equal to 0. So what I'm going to do is I'm going to walk over here. So due to the continuation equation, and since our cross-sectional area of our tank is so much larger than the cross-sectional area of our hole, we can neglect our velocity of point 1. So this will simply become V2 squared. Okay, and then another assumption, I'm not sure if you caught it, I mentioned that the frictional heating is going to be equal to 0. That is one of the assumptions we're going to be making. So our kind of fancy F, the greatest looking, is going to be equal to 0, frictional heating. Okay, I'm going to try and clean everything as we go, just so I don't have to make any cuts. I may have to make a cut to clean up everything, but I'm going to try to maintain it at the level that we're at right now, which is pretty clean. So let's just start moving along with this. Well, what do we know? We know that we want this. I'm just going to tell you that now. We want this V2 equation, which we are going to end with because that will really help us out when figuring out the differential height equation that we're going to need when relating the volumetric flow rates. The volumetric flow rate. Okay, so I've labeled these points 1 and 2. So we need to make sure that we properly note these as 0 and h. So one of these is going to be 0, one of these is going to be h. Now the best way I like to think about this is the top is going to be h and the bottom is going to be 0. If we call this h, then it would not be changing, if you think about that. It's not like it can go any lower, the height, and it's not like it's going up either. And also, if we had 0 up here, 0 would be changing, and that just sounds strange. So for ease, we have h up here because it's going to be going down, and this is just going to be 0 because it's at the bottom of the tank. It's the best way I like to think about it. So what do we have? If we take g to be positive 9.8, what we're going to have is g multiplied by our position 2, which is going to be 0 minus h. So it's going to be minus gh is what this is going to become. Hopefully that makes sense. Okay, and now we've done a pretty good job so far. Pretty much all that we have left are these two terms right here, and then some reorganizing and some relationships, and we'll be left with our expression that we want. So let's start with our pressure at 1. Well, an assumption that I told you earlier is that we know that the initial pressure inside of here is going to be equal to the atmospheric pressure. That's a very important relationship that we need to know. So that's going to be our initial pressure. So let's start and build an initial pressure relationship. Yeah, we'll start to do that. But what we're going to do is we're going to relate that to moles over here, because we know that moles are going to be constant throughout the entire expression. Well, what that can do is that we can figure out this moles of air in terms of our P1, but let's just start with the pressure initially. So I'll just try and explain this as I go. That probably sounded like some word soup, but I'm going to try and explain this through. So what we're going to have our moles of air, which we know to be constant. It is always going to be an n amount of air. That is going to be equal to, I always mess this up, PV equals nRT. So it's going to be, yeah, that's right, PV over RT. So I said this is going to be our initial case is what we're talking about. So this is going to be our atmospheric pressure. As I've said, our initial pressure is going to be equal to the atmospheric pressure. It's just one of the assumptions we're going to make. In addition, we have our initial volume over RT. Now, what is this going to be? Since we are talking about air, our volume is going to be, of course, our cross-sectional area, because this is the piece that we're talking about. When we're talking about this piece, we need to figure out what this area is going to be. Now, what is that, or what this height is going to be? What is that height going to be? That height is going to be the total height minus our initial height of our fluid. That is what's going to be the initial amount of volume of air in there. So what we can do is you can call that AC multiplied by our total height, big H, minus our initial height, HI. What I'll do is I'll simply plug that in right here. Times AC, cross-sectional area, multiplied by our total height minus our initial height. Okay, that looks pretty good, yeah. So now that we have this relationship, what we can do is we can use our moles in another ideal gas equation to figure out our pressure at point 1. So we're going to have our pressure at 1. It's going to be equal to, I'm just making sure I get this right. So it's going to be, yes, it's going to be P equals nRT over V. P1 equals N, which we said was constant. There's no N1 because N is staying the same, over our volume at point 1. Now, just like before, we had our initial volume, but what this is going to become This is going to become our cross-sectional area yet again, but what it's going to be multiplied by is our total height minus our variable height h. So what we're saying is that this point 1 is going to be dropping slowly, differential change in height. It's going to be dropping slowly, so what does that mean? It means that the height of this is going to be dropping at h minus, h minus our variable height h. That is going to be how much height of air that we have in there. Hopefully that makes sense. Sometimes I feel like I over-explain, sometimes I feel like I don't explain enough. Either way. So what we're going to do is we're going to plug that in. Get our cross-sectional area multiplied by big H minus little variable h. Okay, and now that we have this expression, what we can do is we can simply just plug this in. That is going to give us our pressure at point 1. So I'm going to go ahead and get on a knee, if you can still see me. And I am going to put, yes, our P1 equation is going to be equal to, now when looking at this, we're going to have some cancellations, okay? We're going to have that RT cancel, plus we're going to have our cross-sectional areas cancel. So what we're going to be left with is our atmospheric pressure multiplied by our total height minus our initial height over our total height minus our variable height h. That is going to be a very important expression that we have. So what are we left with? All we are left with before reorganizing, trying to solve for V2, is going to be P2. Now what do we need to know about P2? Well, when we're talking about a system that looks like this, what there's going to be is pressure recovery. When talking about the continuation equation, what we had right here was a smaller cross-sectional area and a larger kinetic energy, and then here, I think I said that right, smaller cross-sectional area, larger kinetic energy. Here we're going to have a larger cross-sectional area and a smaller kinetic energy. And what that's called is pressure recovery, which we can see here. This is what our pressure recovery is going to be. When neglecting our change in height h, we're not thinking about that. What we're going to be left with is something like that. There's pressure recovery. However, when talking about a system that looks like ours, which I'll do my best to try and draw this the best I can. It's pretty much, oh, I drew that the wrong way. Oops. That is pretty much what our system is going to look like. We have this can be our part 1, this can be our part 2. Not part 2, or position 1, position 2. When looking at this, there's no pressure recovery at all whatsoever. This is a sudden expansion. There's no, we cannot, this does not happen in this situation because it's such a large sudden expansion that there is no pressure recovery. So what does that mean? That means that our position 2, our pressure is going to be equal to our atmospheric pressure. So, if that makes sense, I mean, just come over here and look. Just because as soon as this drops off, there's no pressure recovery because it's such a small area to such a large sudden expansion. So what it makes logical sense that at this point it's going to be equal to the atmospheric pressure. P2 is going to be equal to our atmospheric pressure. I don't think I explained that very well, but personally when I think about it, I just like to think about it in a logical standpoint. You have a big tank full of liquid, and as soon as you drop out from this small, tiny hole, what you're going to have is the pressure is going to be equal to the atmosphere. It's because it's all surrounding. It's not a gradual change. It's a sudden expansion. So either way, what we know is that this is equal to pressure and atmospheric pressure. Now what we can do is we can start reorganizing this equation. Now what I'm going to do is I'm going to first try and get V2 over here. So what I'm going to do is I'm going to say negative V2 squared over 2 is equal to P2 minus P1 over rho minus GH. Just so that when we plug it in, it's a little bit cleaner. So what I'm going to do is I'm going to make this positive, make this negative, make this positive, make this positive. So what we're going to be left with is V2 squared over 2. I'm actually just going to put the 2 over here is equal to 2. We're going to have P1 minus P2 over rho plus GH, all of them. Now this is already looking pretty dirty, but I'm going to go over here, start plugging this in. So we're going to have is P1 what we can do is we can pull out this PATM. So it's going to be 1 minus 1. So it's going to be this minus 1 with pressure. Okay, here, I'll just start writing this. E2 squared equals 2. What we're going to have is a big bracket. And within that, we're going to have our relationship down here. Oh, 2. Okay, 2. What we're going to have is our pressure atmospheric over rho, because we have that right there. PATMs are canceled. So P1 is going to be, what we're going to have is H minus our initial height over our height minus our variable height minus 1. And I think I should put maybe even another set of brackets. This is just looking confusing right now. Minus 1, what we need to do is we need to multiply by GH, or add GH to it. So I think what I might do is just add another set of brackets plus GH. I think that should, yeah, that works. So then what we do is we take the square root of this nonsense. Oh wow, this got pretty messy pretty quick. Okay. All right, so what I'm going to do is I'm going to rewrite this in a little bit more understandable terms, and then I'll be back, and what we're going to do is we're going to finish up talking about the volumetric flow and how that's going to relate to the expression that we want, which is going to be our differential height over time of our tank until it hits steady state. So I'll be right back. Clean this up for you. All right, so hello everyone, we're back. What I did was I simply rewrote this. It's still not very pretty to look at, but what we're going to be doing, okay, I'll just explain that now. What we're going to be doing is we're going to be going into Collaboratory using Python. We're going to integrate, solve IVP. Initial value problem, what we're going to do is we're going to try and find the differential height over time. So now that we know that, what we're trying to find is an equation for dH over dt. What we can do is we can start to talk about the flow rate and how that's going to get us to that differential height expression. So what do we know? We know that our flow rate going out is going to be equal to, from our continuation equation earlier, it's going to be equal to V2 multiplied by a whole. Okay, what is this going to be equal to? Now this is going to be equal to the negative differential change in our volume over time. Now why is this negative? Because it's leaking out, we're losing volume. Pretty self-explanatory. And what's this going to be equal to? This is where we finally get our term. That is going to be equal to the negative product of our cross-sectional area multiplied by our differential height over differential change in time. Okay, now we're finally getting there. So what we're going to want to do is I'll just so this is the relationship that we know. What we want is dH over dt. So what we're going to get is dH over dt. Just writing this big because we finally did it. We finally got to the end of this problem. This is going to be equal to, got to make this negative, V2 times our area of our hole multiplied, or divided by, sorry, the cross-sectional area of our tank. Okay, so like I said, what we're going to be doing is we're going to be hopping into Python in a minute. And what we're going to be doing is we'll pretty much have an expression for this. Just plug it into here, try and find our differential height over time, and try and find when that reaches steady state, or when the height finally levels out, when there's zero slope in our expression. So thank you for watching this part, and I will see you in a second in Collaboratory. Alright, so hello. What we're going to be doing right now is we're going to be using Collaboratory and Python, also SciPy integrate. And what we're going to be doing is we're going to try and put in our differential equation for our leaking tank, the differential height over time. What we're going to be using is IVP, in accordance with this rather. And we are going to try and solve this initial value problem, and this is going to give us a nice plot of what the height of the liquid is going to look like as it approaches steady state. So let's talk about what we have here so far. First up, we have NumPy, numerical Python. What this is going to be doing is it's going to help us with a couple calculations. I think just a couple things is what we have. We'll get to those. then what we have is we are going to import solve IVP from SciPy integrate, which I have pulled up over here. What this is going to do is it's going to solve an initial value problem for a system of ordinary differential equations. Now, we do not have a system, we only have one, but it is still going to work for us. Now, this is going to integrate a system given an initial value, as I've just said. Now, there's a couple things that we can talk about here. Is the function, the callable function, is going to be in this form, and what we're going to have is we're going to have a few different supplies for it, a few different things we need to give it. We need to give it a time span. We need to give it, well, this is just for SciPy integrate solve IVP. So the first thing we have to do is define a function, but once we get there, this is what we're going to have to do. So we're going to have this function that we're going to call, that we're going to create, and then we're going to have a time span, an initial state, and then we're going to have our method, and then we're going to have a dense output as well, and in the end we're also going to have to go towards an event, which I will explain later. Now, scrolling down, we also have some returns. This is going to supply us with an array, but either way. And then in addition, we need to be able to make the subplot of our graph that we're going to be creating. I've also gathered all of the values, the constants that we're going to need, which is in our homework page. So I just imported all of these real quick. So now what we can do is we can make sure we hit Shift Enter. I always seem to forget, and it always messes me up. So now what we're going to do is we're going to define a function that we're going to be using to put into the SciEvolve IVP to give us the values for our differential equation. So what we're going to do is we can define this as the right-hand side. As looking at this, it is the right-hand side of our equation. What are we going to supply this with? The typical, the t and y, colon. Now what do we need to do? We also need to add that y is going to be equal to h of, wrong way. So our height is going to be our y of 0, and we need an array because we're going to be supplying an array, if that makes sense, for our solve IVP. Now what we need to do is we need to add our velocity at the exit, which we're calling v2, so that we can return a value in accordance with our differential equation, and that's going to give us the slope at each point, which I will exemplify. So what I've done is I've gone ahead and I've done this, put this here for ease of access for us, so I don't need to explain it while I do it. But pretty much this is just the exact same thing that I've derived in the first part of this video, as you must have seen about 3 minutes ago at this point. And I've also added the np.square root, which is going to be using the numerical Python, and that is going to give us the square root of all of this, which goes in accordance with all of the numbers that we have here, all of the constants that we have. So now what we need to do is we need to return an array, if I can spell return correctly. And I seemed to mess this up last time, so it's going to be negative, I believe it's a whole, multiplied by v2, divided by AC, which is our cross-sectional area of our entire tank. And the a-hole is the cross-sectional area of our hole. If we hit Shift Enter, should be all good. Now what we can do is we can supply a value. Let's say initial time is going to be 0.5 seconds in. We can say set it as hi. Oh, did I mess something up? H equals y0. Choose back 0.5 hi. Oh, that's meant to be an array. Is that what I did wrong? Okay, that's what my bad. Okay. So what this is saying is that this is the differential height in meters with respect to time, saying that it is decreasing, which is hopefully correct. If we think about it, it's going to be a curve going downwards. Okay, so we can get rid of this. Now that we know that this is working, well, we're hoping that it's working, and it is. What we can do is we can hop straight into solve IVP. Now looking at this, what do we need to supply it? We're going to supply it with our function, the right-hand side, our time span, which is going to be from 0 to t end. I don't know why that t didn't type. Putting that within parentheses because that's a time span. We need our initial, which is going to be our initial height is going to be our initial value. Method, we are going to use the radu method. Radu, however you prefer to pronounce it. I spelled this wrong last time and it put me in a pickle. And then last thing we need is we're going to go for dense underscore output. is going to be equal to true. Now, this looks like it's an issue. Well, it is an issue. We're going to fix that later. What this is saying is that we have an invalid value encountered in our square root. Now, should I explain this now? I guess I'll just explain this now. This will save us a little bit of time later. So when looking at this right here, as time progresses, what's going to happen is this h right here is going to keep... Sorry, I bumped the camera. I hope you can still see. But this initial height right here and this height right here, this changing height, what this is saying is invalid value means that there's going to be something wrong with this equation right here, specifically within this piece right here. Okay? So what this is saying is that our total height minus our initial height, that's already going to be a pretty small value. And as our fluid level keeps decreasing and decreasing and decreasing, this is going to be getting smaller and smaller. Then multiply and then subtract 1 from this, that's going to make it even worse. Now luckily we add GH to it, but once you hit a certain point, that's not going to be able to make up for the fact that this is going to be a negative number. As soon as this piece right here goes negative, this 2 cannot salvage it. Whenever this changing height gets to a certain value where it's no longer changing, where it hits that flat value, it's going to end up that this is going to end up being negative. Didn't really explain that well, so I'll just give it another quick try. Since we have our height that is decreasing right here, and this is barely a positive number right here, okay? And then as this is getting smaller and smaller, this whole thing is getting smaller and smaller. And once you hit a certain point, this GH value is not going to be able to turn this positive. And in the end, what you're going to be left with is a negative number under here, which I'm not going to do this now, but that's what we're going to need later. Is we are going to need, that is why, as I mentioned, we are going to need, if I can find it, is this events. This is basically going to, what does it say? Whether it's going to terminate once we hit 0. Okay. Either way, for now, we're not worried about that. So what we're going to do is we can simply just put our time frame to 1 second. And we should be okay. So what we can do is we can say z is equal to this. And we can also say, let's say z at 0.2 seconds. Let's see what the height of our fluid is at that time. Did I do something wrong? 1. Result object is not callable. Oh, sorry. Z dot sol. There we go. Forgot that. So that's saying what the height is at 0.2 seconds. Because what we've done is we've integrated. So that is going to be, we had our differential height with respect to time, and what this is going to give us is the height with respect to time right here. Okay, now this is where I get a little finicky sometimes, is making the subplots, because you got to be very particular about this. So let's say that fig is equal to make underscore subplots. And then actually before that, what we'll do is we'll make our t-plot is going to be equal to np.linspace, and what this does, it's going to say right here, it's going to return evenly spaced numbers over a specified time interval. So we're going to go from 0 to tn, I believe I called it, and we're going to say that there's 500 evenly spaced points between that. What is this going to do? We're going to basically plot this z right here. So I had the 0.2 seconds. We're going to be plotting this at a plethora of different values so that it gives us a smooth curve for our graph, which we are going to see. Okay, so now we have fig equals make subplots. What we're going to do is we're going to go to fig add, I believe it's add scatter. It's not scatter plot. I don't know. Yeah, fig add scatter. Now what are our supplies going to be? Oh man, there's a lot of them. So basically what we're going to have is we're going to have x is going to be equal to rt plot, and y is going to be equal to z, it's going to be z.sol, I think it's z.sol, and we need to provide it with our, we need to supply it with our t-plot. Okay, and I hope that that worked. See, this stuff gets a little fishy for me, but either way. Then we're going to do is we're going to fig dot update, is it update layout? There it is. what we can do is we can try and make this look pretty if it even works, which I'm praying it does. 600, you can make that smaller. If I can spell a height, it's going to be equal to 500. And then what we can also do is we can say, oh, it's not layout. Is it template? Yes. Plotly underscore dark. Now we pray that this works. Oh, wow. I'm not surprised at all. That's what I meant to say. And as you can see, we have a dark subplot. I'm actually going to bump this up. Let's just say 700 real quick, just so we can make it look nice. It's pretty big, but we'll live. Okay, so what do we have? We have an issue. Clearly, there's no line on here. Now, why is that? Now, when we're looking up to here, we need to understand that our z is taking in an array. So what we need to actually do is we need to supply this with an array so that we can end up with this right here. Okay, so now that we have this right here, what we can do is we can try and play around with it. Now, as we saw before, when we did the 10 seconds, we reached that error of having too much time. It goes to 0, and then it can no longer run itself. So what I'm going to do is we'll put that to 5 seconds, and we're going to pray. Well, still, again, it must not contain infinites. Traceback. Invalid encountered in square root, meaning that meaning that it goes to 0 between, I'd say, about 4.4 to 4.6 seconds, somewhere in that range, is where we're going to be hitting that 0. So what I'm going to do is I'm going to do a quick break, and then I'll be right back. Alright, so hello everyone, and we're back. And what we're going to be doing is we're going to be finishing this up now to the best of our ability. So looking at this, what we have here, what we realized, well, this looks good, but let's actually mess this up real quick. Let's go through, and we notice that we have this invalid value in our square root, because, again, what we have in here is that this is eventually going to hit 0. The velocity of the fluid going out is going to be 0. It can never be negative. The water can't just be being dripped back in, if you'd rather, because it's very slow. Now, why is that? As I've tried to explain, is that this value right here, these values right here are eventually going to hit 0, because these are all within this value specifically right here. It's going to hit 0. Now, why is that? Because our initial height, this value is already so small. It's equal to 0.1. Our initial height is 1. This is 0.9. And as you make the total height subtracted by this, smaller and smaller and smaller, it's eventually going to get to the point where while this value gets smaller and smaller, this is eventually going to hit 0 and then to negative numbers. So what we need to do is we need to call an event into this, which, as you can see right here, this is going to be the appropriate way to do this. So here we are. This is what we're going to do. Each event occurs at the zeros of a continuous function. We must have it in the signature, this same style as our as this right here. We're going to have it in the same format as we have. We need to define. We'll call it our V2 event. When the V2 of velocity, pretty straightforward. The V2 that we have up here is what's within here is going to be equal to 0. So let's just go ahead and do this. So it's pretty much going to be the same format up until we get to here, which we are going to have a return, which is going to be not an array. That is one difference that we have. So we have 2 on the left, 2 on the right. That should be proper syntax. Then what we need to do is we need to specify that our V2 event is going to end equal to true. Hopefully all that syntax lines up. And now what we can do here is we can actually add our events is equal to, put it in brackets, our V2 events. Now let's actually just go through and do this real quick. Now I had this problem just now, and I'm hoping that it's fixed. See, I don't know why our value for the T event is wrong. Is it because... That's so weird. What if I just take... I'll just take the whole thing then. I'll take all the parentheses. See, I know that what the number is supposed to be, and this is not where our event is supposed to occur. This array right here. That is not where our event is supposed to occur. So I'm hoping that I didn't do anything wrong with this, because I really don't believe I have. And if that's something I have to take, then that's something I'm going to have to take. But so long as this works, that's really what matters. There's probably just some small bug within the code. I don't really know what that could be. Just glancing around, I think all my values look correct. But either way, yeah, either way, we're just probably going to accept it. But let's just move on. So now that we have this, it's going to say that we have a terminal event that has happened here. And this is going to be a part of our Z now. So what we can do is we can place, instead of this tn, what we're going to do is we have, I'm actually going to restart this. And we need our endpoint. So what we're going to do, as I believe what we do is we do n or z dots z dot t event. What we're going to need to supply it, as you can see, is we have two different arrays. So we're going to need to supply it with two different arrays. And then that should work, and it did not work yet again. Okay, so real quick in the last part, what we noticed was that I was having some issues with my code. I cannot figure out what's wrong with this array. I even tried switching up some of these floats, some of these different things that I have in here, double checking all my values, and again, I could not get it to work correctly. Either way, what I have found is that looking at this, it's T events rather than it's T events, which I completely misread, and I had that T event was and the two different arrays. So what it is it's T events. And what I end up with is this really weird lip right here. Now the value is supposed to be somewhere in, I think it's like 4, it's somewhere right when this gets to flat. So somewhere around 4.49. Again, looking through my code, if you see anything that's wrong, please go ahead and tell me. I could not figure it out, but this is what we end up with for our plot minus right around here, that little extra lip that we have. So I thank you for watching, and I'll see you next time.